Hello everyone, we'll get started. Welcome to the April Infracoders meetup for 2015. This is actually our third year, so this is our 37th meetup consecutive, which is pretty cool.
This one.
Message Media is hosting us, so thank you very much for that. You're welcome. And just in case you don't know who Message Media is.
All right. Hello, I'm Justin. I'm the CTO here. I believe I've got a minute to share some information with you. Who's heard of Message Media before this evening? That's not so many. But I'd guess at least 75% of you have a text message on your phone that we've delivered about some sort of hairdressing appointment or any sort of reminder. We send millions and millions of messages a month. In fact, we sent over 1 billion messages in the past year. We are growing very quickly. At the moment, we're going through a massive transformation project where we're rebuilding our core message sending gateway. There's one statistic I just wanted to share. Twitter, at average, peak load is 350,000 messages a minute. We're going to do 50,000 messages a minute at peak. Okay, it's quite a difference, but the reason I share that stat, just to give you an idea of how many messages we process on a global scale. Very, very interesting project we're working on. These are the technologies we work with. You probably recognize a few of those. And that's everything from me. I think that's in a minute. Have fun.
Great. Thanks, Justin. First up, we've got Sam talking about his crazy SSD thing, NAS. So once in Chromecast.
How do I Google? No, doesn't just work.
Yeah, can you do?
No, it doesn't.
Can you do configuration manage streaming?
This thing is the Chrome plugin thing just crashes and Chrome's locked up.
Getting our tech support guy.
Yeah, I think so. Yeah.
You're an IT guy.
Just give me an HDMI cable. Yeah, it all cracked out again. Okay, awesome. Thanks. You're a legend.
Fingers crossed.
All right. I should have watched what you've done. So. Here we go. All right. Okay, I kind of wrote these yesterday. I was not expecting to do a full-on talk because I'm just going to do like a 15-minute or less, probably 5-minute talk about this. But I've been working with some interesting storage concepts. Work for a company called Info Exchange. We don't work in storage or anything like that, but we have really limited funding because we're a not-for-profit agency. So any way in which we can sort of think differently man, someone should trademark that. So, to do things in a maybe different way that can be valued that we can pass down to other not-for-profits with services is a great thing. So I'm going to propose something that we stop talking about price per gigabyte because it's only really relevant in some very, very small situations in reality. It is relevant in some, so I'm not saying that doesn't matter and there's never a use case for it because that's crazy. But in a lot of businesses, from what I've looked at, it really is sort of the wrong kind of metric when you're looking at purchasing or designing a storage system. I think we need to talk about dollar per IOP, unless you really don't need performance. Obviously, it doesn't matter if you've got some app that doesn't really touch disk or that's not an issue for you. Hopefully, get something out of the talk anyway. Go over why IOPS matter. Obviously, people talk about IOPS as being a performance thing. What they generally don't talk about is the data safety. So databases almost solely rely on small small random bytes and reads from disk. And we know that in-flight data is a risk. So people talk about like UPSs and the amount of time that it takes for, say, a server to cleanly flush data out to disk if there's a disaster or whatever. What often isn't discussed is the amount of time that, particularly on these proprietary RAID controllers and things, the time that data is actually sort of at risk while it's in flight in either the buffers or the caches. It's almost never discussed, which is really, really weird. Particularly when I guess there's now options for spending way less time or reducing complexity by not having things go through that same process. I'll explain a bit more on that in a minute. Our recent statistic, everyone loves quoting Amazon. Amazon found that every 100 milliseconds of latency cost them 1% in sales. So I'll start with our kind of existing solution, quote unquote, pretty standard sort of small business sort of stuff, you know, some kit somewhere. We're not in the cloud because a lot of our business model is based on government organisations, NGO, health sector and stuff that don't want to put their data or aren't legally allowed to put their data on Amazon or whatever. We do have some servers and rack space in that, but a lot of our, I guess, our price points and stuff like that are also, we're more efficient having our own data centre because we're a not-for-profit. We get massive discounts on things like power and rack hosting and stuff like that. Otherwise, might be a serious concern. Our existing units are pretty standard, HP units through and through, 2,000 to 4,000 IOPS 4K random writes per unit, and they use about 250 to 280 watts on idle. They're hot enough to cook an egg on. I know that these things go up to like 600 watts. They're insane. The management app for it is disgusting. It's Java on Windows. The ILO, the remote administration, if something craps out and you have to remote it, it's really, really important. It requires you to run IE6 or IE8 on a Windows browser. There's no access to the underlying OS or tools. So if something really goes wrong, you're at the mercy of trying to push through level 1, level 2, level 3 support at HP. And look, I'm not having a go at HP. You can replace that with many things. There's no additional per node capacity. So you can't open those up and go, shit, we might add some SSDs and or some larger disks. Let's fill up those PCI bays that are sitting there. It won't support it. There's no license for it. $50,000 for 10K IOPS. Units are about 20,000 a node, about half that. You run into things with proprietary software, which are rather interesting. This was me performing an upgrade just a couple of weekends ago. While upgrading the SAN units one by one, the latest firmware, we noticed that the upgrade process, it says here, begin main install _ saniq.sh. Sounds really, really good. And getting the host name from S1SAN4, which is the host name. That is the absolute tip of the iceberg with how poorly designed many of these large vendor products are. When there's a problem with something like this, let's say a node has applied some updates, it's done its testing, it's rebooted, it's started doing its testing. If it doesn't reboot fast enough because it's discussing around CentOS 5 or something under the bonnet, it takes reboot, you're kind of stuffed. The upgrade process throws a mental and it says, oh, it timed out, sorry. And you're sitting there in production going, let me just refresh, and then Java crashes. Quite seriously, it does. It just starts crashing. So you reopen it and goes, oh, you're in a funny state. Let's try doing this again. I think Ross in the back there rebooted the SANs 25 times to get the damn thing to work. We ended up rooting the SANs, getting root on the boxes using a script off GitHub, which generates, based on the MAC address and a couple other things, gives you root access, essentially, because we call HP, and they don't care, essentially. Right? They don't really care. We're not a big company with millions of dollars, and there's not some, like, you know, guy coming over to us and going, oh, you know, you got to look after these guys, they're great. What happens is you get through to someone, so a technician calls you back, they have a 4-hour on-site, which is the minimum on-site response. The guy turns up and he goes, oh, I don't know, I'll have to call Texas. And that's pretty much it. That's what you get. They don't know. We watched them remoting in one time into the SANs, and I think today. Yeah, this was a great one. So production system, one of the units in the Java console, which is the only way you've got managing them, just disappeared. Still functioning, still serving up requests. Production, patient management system, yes, it's clustered both in the device and across multiple. It just disappeared. And I'm what the hell? I called them up, and it's still functioning. I go, look, this is kind of bad, it's this. And they said, okay, what we're going to do, I actually don't know what we're going to do. I'll call someone else. 4 or 5 hours with not having any access to our production data to manage it. We're still serving requests. They finally went through to like a level 3 technician who was in Texas. Really nice guy. Knew what he was doing. He's like, okay, to be honest, we need to reboot these things. I said, whoa, this is in production. Usually I'm fine with it, but we don't know what the state is. He said, what I'm going to do is I'm going to get a team of engineers together, and we're going to go through all the logs and make sure you're in a state that's safe to reboot one of these nodes. And I said, okay. And the business said, okay, we'll wear that risk. It's a sensible thing. It's bad if it drops out completely. What happens? They reboot it. It's like, That's okay, cool. And the two other technicians that were on the conference call disappeared because they've got other jobs to do and we're not making them any money. This guy was left in the room. Our entire production system locks up because somehow what they did caused a split brain. They didn't really understand the system properly. The technician, as you can see here, just goes, "Oh no, it's going to be one of those days." I'm really glad I'm in Texas, not Melbourne, because these guys have been really into this. So I've seen that sort of thing, and yeah, again, just you want to install our toolbar on your SAM? Do you care about your data? Like full text searching across the storage. So I think we don't work for these tools, right? So let's make the tools work for us. We're a group of highly technical individuals that meet up quite regularly, in DevOps community, Infracoders and stuff like that. We think managing things in code is kind of nice in many situations. We like to be able to automate things, that kind of stuff. Surely there must be a better way to do this. So what I propose is that we use standard tools with modern technology and open source the design for critique, and so that other people can learn and experience. So you don't have these special experts that you have to fight through multiple tiers to get access to. So the idea is kind of break the rules of enterprise storage and all the marketing that goes around that about them being safe because they've spent 20 years understanding how to write stuff out to disk and you're safe for your data with them and you can totally outsource accountability and all your problems. But not at the expense of safety. This doesn't mean being a cowboy and throwing something together and go, "Oh, that's fast, cool, that's great, yeah, it'll totally be fine." And then suddenly your data's kind of nowhere, it's not committed, and you never really know where it is. It's not one of those. So the modern landscape to me, automated provisioning, vendor neutral, seems like a no-brainer. Lower total cost of ownership. So this is something that gets pushed a lot. A lot of the reason that companies will go to Amazon or Rackspace or something because in their business case, it'll save them a lot of money. It totally does. In some business cases, obviously, the same people go there and go, "Holy shit, now we have to employ a full-time person just to look after all the instances that we don't know where the money is going," and oh my God, right? Regardless of that, you're probably still going to have some localized infrastructure in many companies. Maybe not a small startup. Standard components and software, like if it dies, I don't want to have to wait for something to be shipped from China as a replacement part. And modular scalability. So, I mean in the software and the hardware sense. If a unit dies, instead we can add an extra one. Say we want to go, okay, we've got 2 terabytes of storage, which is not much, but say it's a tier 1 storage system, 2 terabytes useful, we want to go to 16. What are we going to do, right? Can you just slot them in? Do they take a piece of space? Is there any power concerns? That kind of thing. And the software side. And this is the bit that's really interesting to me, is break the $100 for 10K IOPS barrier. So if you think back to that original SAM, which is a pretty standard low-end, small, medium business SAM, you're looking at $50,000 to get the IOPS that I'm talking about. In fact, a lot more. The solution must be resilient. Aim for 1 million IOPS per node. So 1 million. And when you say, "Oh yeah, but that'll be streaming, read writes." No, 1 million. I want 1 million 4K random read IOPS database operations per node. I want reduced latency and the time and flight to be greatly reduced. I don't want stuff sitting in a cache and then I lose power and some proprietary RAID controller goes, "Oh, that's gone, sorry." I don't want it to be so slow or the latency to be so high that you have to buffer up a huge amount of writes before it actually gets flushed to disk. And it's fun to shake up these writes. So talking about the kind of hardware that we looked at, spent a long arduous time trying different pieces of hardware and different solutions and different connections and things like that. I've been kind of on board with the NVMe stuff for quite some time, quite interested in that. You've probably seen an explosion in that probably in the last 3 weeks because I think a few things have posted Hacker News. There's that kind of effect happens. So suddenly everyone's talking about NVMe, the new Mac, the Mac laptop just came out. They didn't even say it anymore, but it's actually NVMe storage. It has no AHCI, no SCSI layer. It's pure NVMe, so it writes to a PCIe storage. So these are an interesting unit. They're bloody expensive. They're about 75% of my design per node of the cost. That's the DC3600. There are various vendors that make kind of equivalent drives, not just pushing Intel. There's other people that do it. I think the Intel stuff's really high grade, very high performance PCIe NVMe drive. Then you've got like a tier 2 style storage. You're like the SATA SanDisks, right? You can buy these from PC Games here, right? Are they in your gaming rig and are they in your SAM? Now they are. I'm not suggesting go and buy bloody shitty Samsung 850 Pros or something like that. Those are the best SATA SSDs you can buy. And you can only get the Extreme Pro 3s from SanDisk. They are really highly rated. They come with a 10-year warranty, not that it means much there. I'll go into that a bit further. Standard Intel motherboard. I don't want some bloody crazy HP thing with bits of plastic hanging out of it that I have to buy a license for to replace or upgrade. These, has anyone seen one of these? Anyone know what it is? No. It's a SATA DOM. So that is essentially another solid state. It's a tiny little, this one here is really small, it's just a 16 gig, and that sits on 2 special slots in the motherboard. It's just straight SATA with power, hence the yellow connector. And that can act as a host operating system. So you generally chuck 2 of those in RAID 1, they don't get any writes, local logs, that kind of thing. And then we decided, after much deliberation through many different vendors, we've actually gone with Supermicro for the servers. Supermicro are the ones that supply all of Yahoo's data center, a lot of Facebook's before they do their open compute stuff, all of Intel's data centers, big stuff. It's all data center stuff. You don't see heaps of it in Australia because it's generally really large scale and generally like HAS providers and stuff like that will use it. Interesting here. So NVMe that I touched on, essentially it's, some of you, as I said, have probably heard about it. Basically, it replaces the need for the AHCI layer of storage in the Linux kernel, and I think Windows supports it as well. If you look at the complexity and the number of layers in it, this is totally high-level stuff, and I'm not going to go into great detail here. It reduces complexity, it reduces latency tenfold, massive difference, and your throughput is much higher while having a lot more concurrency. For example, I'm not sure how many of you know about interrupts and stuff like that. AHCI is limited to 1 interrupt. NVMe has 2,048 interrupts, and that's over MSIX. So I'm not going to go on that for ages because most people don't find that particularly interesting.
That's 3 times 20.
Come on, Chrome. No, Google wants this stuff out. So yeah, the 2 drives. If you're talking high values, because if we think about 10 years ago, you're like, oh, SSDs, they're fast and stuff like that, but they don't last very long. You don't want to put mission critical stuff in them. You don't want to thrash them or use them as a cache or something like B cache or whatever, because they're going to die. It's now gone completely the opposite way, where their lifespan and life expectancy, the write time is much higher than spinning disks now, and that's just going to keep going really quick. So if you look, 228 years mean time between failures. It wasn't that long ago that we were looking at Seagate disks that had a mean time between failures of 8 years. Where is it? Never buy a Chromecast. What is this? Oh! Yeah, cool. Board room. Yeah, maybe.
Yeah,
Yeah, that's only part of it. Where's the other dude?
Yeah. Wait, is it that?
It's only back for 1 app.
For the table.
No, it's only back for 1 app. What is it? Is that the pass this? Hey, you know what? And no, it's not.
While we're waiting.
Yeah, you can ask me questions and stuff. I'm sorry, I'm operating on like no sleep, and I'm just about to get on the flight. So.
One thing I will say about the NVMe stuff, which is really cool. So I've been finding that for a while. So it's like, yeah, $4,000 PCI Express card. I'm going to buy that for my computer. But what they've done is actually made the 750 series of those cards.
Correct.
Yeah, so the cost is less. We're still talking like 200,000 IOPS from a PCI Express card, over 2 gig a second read, and maybe like a gig write sort of deal.
And those ones you can buy from PC Case here or whatever, and they're $1,500, which is still a lot of money. Yeah, so just keep it
There is an information like that.
Oh, I tried. All wired and stuff. So, you don't anything about Chromecast?
Yeah, I was actually looking at the 400 quid one, like $600. Like I can swing it.
Yeah.
I don't know if I want to.
Oh my god, it works. Can someone please endorse me on LinkedIn for Chromecast? Please. Gary Friends will be all over me. It's a rare treat. Okay. So back to it. Shut up. Shut up, Francois. Endurance. That endurance. 8.6 petabytes written. That's a hell of a lot of data to write. Remember that your database operations in general database like 75, 8% read anyway. Obviously, your mileage may vary depending on what kind of, uncorrectable error bit rate. Yeah, it's really bloody good. 5-year warranty on those, so that's not really an issue because HP is going to sell you or whoever's going to sell you a 1-year thing, and then you'll be paying an extra bloody 5K per unit per year for anything over 3 years. I don't really aim to have these in 3 years' time because I think we're going to outgrow them pretty quickly. And then the 480s are great as well, but 228 years. You're not going to get that, obviously, and you get obviously you have DOAs and stuff like that. But it's pretty impressive just to think where we've come from in a short time, and it's not Samsung. Never buy Samsung. Resiliency. So node-to-node replication and failover. So let's keep it really simple here because we can expand this. There's just 2 nodes, A and B. Neither are primary or slave. You have replication between the 2, and it's on a per LUN basis. So you could do, keep it really simple here. Multiple LUNs, load balance between 2 units. You've got, application A over here running off this one and replicating to the other unit, and application B over here running from this one. So it's decent. It's not perfect, but it's sort of like a round robin replication. No proprietary RAID controls or drivers. Really, really super important. It's not just like a Linux zealot. I don't want closed source people to make money. It's time after time after time I've seen data centers, RAID controllers, proprietary hardware, either hold companies back, look at all the people who are stuck on RHEL 6, RHEL 5, and cause massive problems. So, your RAID array dies, it's made up of 2 RAID controllers, suddenly you can't get it anymore because that vendor wants to sell you the upgraded model. Turns out the firmware metadata isn't quite compatible, so you have to backwards flash it. Something you're spending days of your time to try and make that system work. Low latency, as I mentioned before. So we want network resiliency, storage resiliency, node resiliency, and if you want site-to-site replication or resiliency. So node topology. Cool. Really simple. 2 tiers of storage and the ones that we're using. Now, this is a use case for us. This isn't saying this is how you should do it or anything like that. This is just what I'm doing for what we need right now. 2 tiers of storage. Really bloody fast storage and really fast storage. So the really bloody fast storage is 1.2 up to 2.6 terabyte NVMe SSDs, PCIe. They're on RAID 1, just for the hardware level redundancy. Yes, cool, they've got a great lifespan, all that stuff, but shit happens. You get DOAs, whatever. Someone spills milk on the server and one of them gets fried. I don't know what happens to your data center. RAID, keep it simple. Kernel level RAID. We are not using any proprietary stuff. MDATM RAID in the Linux kernel is nothing like it was 10 years ago, where it's slow and it's a memory hog or anything like that. It's not like that, especially when you're dealing with low latency transactions. If you're dealing with high latency stuff where you're putting a lot in, memory buffers and stuff like that, you've got a lot of that in-flight risk sitting in your kernel memory and shared buffers sitting on the servers at risk. That's not the case anymore with NVMe. LVM, simple. Everyone uses it. Don't. Probably should. I don't know. Really simple. That's done on a per LUN basis. And then DRBD, absolutely standard for replicating between physical devices or block devices. So DRBD runs on a per logical volume. So logical volume exists. DRBD replicates that to either another machine, another site, whatever. Really simple stuff. Nothing really complex or strange complex files or anything. RAID 1 array, RAID 10 array in this case, just full of your commodity SSDs. In this case, we've got 8 because we've got 8 spare slots in the current machine. And the RAID 10 array, exactly the same setup. And then we use iSCSI. Lots of people use Fibre Channel or InfiniBand or whatever. It doesn't really matter because it's just another open source technology. As long as you can get an initiator for it from your distro of choice, then go for it. One thing to probably note about that is when you're looking at the initiators, it's pretty key to think about when these initiators or how they control flushing writes to disk. iSCSI can be quite good if you set it up right, which is the default is quite the same, so it will actually sync all writes to disk. Big thing you can't see, but basically there's 2 nodes in action with a switch and some VMs and things. Brush over this really quickly because text is small here. It's 100% configured in code. There's nothing basically you do outside code. So the DRBD, the RAID, everything, and this is all this is really kind of gross because it's me testing things, but this is just literally a screenshot of my YAML that goes and sets it up. You can use Puppet. I suppose you could use it with Ansible if you wanted to port modules and things like that to it. We're using Puppet because we have that everywhere. Standard hire manifests. Write down a really simple example is how it sets up the RAID arrays, number of devices, what you want to call the array, what array level it is, and the same going down to the NVMe drives, things like that. Nothing crazy, nothing weird. Even the iSCSI targets all just configured in, simple as. And the default action is non-destructive, so if someone goes and puts some typo in there, it's not going to go and destroy your data or destroy your RAID array just because someone did a typo. And the same goes with the network. I won't brush over this because there's lots of numbers and things. This is the defaults that sit behind the scenes that you can override. So, virtual IPs that sit between the two nodes and things. So performance-wise, so I was aiming for 1 million IOPS. It's pretty crazy. So obviously this is pretty early on. Like I've only sort of put these into the testing phase the last 2 weeks. And there's a lot to test on that. So lots of numbers and pretty colors and stuff. What's probably important is here's your $20,000 exam from HP. Here is your tier 2 storage. Here's your tier 1 storage. Here's the total of what each individual unit can provide. Old SAM, about 3,500 read IOPS, 2,500 write IOPS. Tier 2 storage, 324,000 IOPS read and 160,000 write. That's sustained average, 4K, small writes. That's not some streaming amount. That's not burst. That's not the most I've seen on it. That is without crazy tuning or anything like that. That's really good performance. Tier 1 NVMe performance. IOPS, 900,000 read IOPS. Almost 1 million IOPS read performance out of that RAID 1 array. And about 80,000 write IOPS because it's RAID 1 array. There's only 2 units. You can get 3700. The 3700 model SSD does like 4 times the amount of write IOPS and the same reads. It's like an extra $1,000 a unit. Don't need it in my databases. And the total, notice that what's really important here is this is the misconception of how kernel RAID works. There is no noticeable added overhead of say doing those same benchmarks on my NVMe RAID array there and the 480 gig sort of solid state SATA drives there. I can run them both at the same time with the same bloody results. They share completely separate interrupts and they're on different PCIe buses. So you don't get collisions. You don't say if you're maxing out the NVMe drives doing some RAID rebuild or something like that, you're not going to hurt your tier 2 storage, which is much cheaper and maybe your slower apps are on those more. Lots of good stuff. Numbers, big numbers. So the most I can get out of them combined, out of reading from both of them at the same time, 4K random read IOPS, 1.224 million read IOPS, sustained average. And write, 240,000 write IOPS. Megabytes per second. I don't really care about this figure that much. It's not relevant to us. And there's probably ways to get higher, just straight throughput if you're interested in that. But basically, I can do a sustained read of 5 gigabytes per second from any individual node. Really important is the latency. So if you look at the latency, the average, so we're looking at like 20 milliseconds for the old SAMs. We're looking at 4 milliseconds for the tier 2 cheaper RAID array, very, very cheap. And 60 microseconds for the NVMe storage. It's really nicely low. Power consumption, really important if you have a data center and you pay money for it. 100 watt idle for a unit. That's including dual redundant power supplies, 2 CPUs, RAM, everything you need, the disks, everything. They're cold as anything. They're just cold. The fans are sitting there doing nothing. 180 watts peak when I'm absolutely benchmarking all the drives for 4 hours trying to fill these things. It's nothing. Cost. I did Steve Jobs thing. Oh, it's too laggy. 10K a node. So that is actually US dollars because it fluctuates a little bit. Given, when I bought these, I think it worked out to total cost was about 23,000 Australian. It's probably about 25 now because. But that's what's really interesting is that's $100 for 10K IOPS, not $50,000. So even if part of this is wrong, even if I was exaggerating about any part of this, and you were to say it only performs half as good as that, that is shitloads better than these off-the-shelf solutions. it is highly redundant. The part I have not tested or tried yet is the iSCSI failover mechanisms, so pacemaker or whatever we're going to use, chorusing for that sort of level with the DRBD. Haven't tried it, not there yet. Scalable, really easy. So the bonus of this, it's a 1U unit. It's tiny. It's not. It doesn't even fit a whole rack. You can use shallow racks on it. It takes about half a rack, half a rack depth. Quiet, even for a 1U unit. And it's managed in code. So when you go and spin up your instance or whatever, you can spin up your instance in code in the same way in your Amazon instance, because you can use DRBD there if you want to, and you can use all your other replication methods and MDATM on the new, so they've got their new flash high-speed storage with 20,000 IOPS that you pay like $1 million an hour for. This same code will work on that provision. There's nothing revolutionary about this code. It's all standard pretty much public interface. I don't know why no one's really done this yet. This will look like pretty boring. So I don't have all the flash like metal bars like HP has or anything like that, but it's standard components. It's commodity hardware. It's reliable, and I think time will tell, but our aim is to try and get rid of all spinning disks from our data center. So now I'm happy to take any questions or anything. Keep in mind, I'm pretty brain fried from little sleep, no doubt, jumping on a plane and arriving in another country at 4 AM. So all the code for this will eventually be up on GitHub. Most of it will actually be links to other standard Puppet modules, or whatever. There's no crazy application we've written to do any of this. It's really more like a how-to guide, and we did this, and it does work, and this is the testing that we did to prove that it's not shit, and that you won't get split brain, and all that kind of stuff. So there's nothing that we've sort of invented out of nowhere. And I'll eventually put it up there when I finalise it, because I don't want to put anything up and kind of mislead people into thinking that this is perfectly safe, this thing, without it actually being tested. So yeah, that's that. I'm sorry about the broadcast. Who's been watching the NDMA movement out of interest? Just one person. Who's heard of it? Okay. Well, yeah. he's sitting there in the weekend line. What is this? Yeah, okay, cool. Keep your eye on it. Really interesting stuff. You're going to see it everywhere. As I said, even the latest MacBook has it. So do you want to take your luck with the Chromecast? No questions.
That's the best option.
Yeah.
Look, around the actual file system side of things,
Yep.
if you look at ButterFS or
Yep.
ZFS as a consideration.
These run no file systems on, other than the actual host OS. It's giving out raw LVM volumes over iSCSI. So what you do on your client, yes, of course you can do it, but what you do on your client side is your business. For example, we have some Docker hosts, a lot of Docker hosts, and they run BTRFS, and that's provisioned on top of iSCSI. Yes, you could provision BTRFS and replicate it out to some other node or whatever. I found generally the performance is best when you're doing a file system on the client side. It also leaves you, because it's more simple on the server side, you can be a bit more agile with your storage and go, shit, we need to replicate this to another site. Oh, cool, we'll just replicate the RBD because that's already there, and we don't need to worry about file systems. And what if there's some, we've used BTRFS a lot, but what if there's some weird bug that when you hit like 1 million layers or something like that, we hit recently, where there's some reboot happens. So you don't really want, I don't really want that happening at my storage level.
Yeah, no, I hadn't thought of that for the storage box. I was thinking more the block level redundancy. I mean,
look,
going
it's
so
you.
fast, which is awesome, but
yeah, well, look, for us, the
is that a bonus
DRBD
feature? Does it slow you down? Those kind of things.
The DRBD doesn't have much of an impact as far as performance go. I have two in the design. I've got 2 network cards. So one is the onboard NIC, and that is 10 gig just Ethernet. Okay, so Ethernet's pretty crap latency, so we don't actually use that going back to our core switches. That 10 gig Ethernet, it's two Ethernet cables, Cat6, whatever hyperspeed Cat6 is. Just literally they're like that long, running to the unit above it, and that's used purely for DRBD replication. Do you have to do that? No, but I found I had a free PCI slot, so why not? Yeah. And then the real networking, we use DAC, direct attached copper cable, straight back to split Juniper core. So from each node, there's 2 10 gig back ports that in LACP bond, they go to 2 different nodes in a virtual chassis. So you can pull either one out or whatever. So the replication is kind of set. This is diverging from your question. But,
No.
So we also are replicating the DRBD between 2 sites. There was an awful article written recently by GitLab, who are awesome, but they failed at replicating between two countries with DRBD going from their data center to Amazon. Like, why is it slow? So we're using block level replications. It's designed for very specific things in a very simple way, and it works bloody well. The replication between the two nodes over the network connection, I get around about 600 megs a second between the two nodes without it impacting any performance of the actual reads and writes function of the storage service. And yeah, we'll see how that goes. I don't need that much, to be honest, especially if you're doing mostly reads. It's just going to be the delta of whatever you write. So.
What mode is you running?
So the standard, which is what, C?
There's like
C. It's the standard, like 99% of people use C. So it means that you don't have to commit your write to the second node in order for it to be committed on the first node. So your database, say your second node's unplugged, your database won't stop and wait for the second node to come back online before it can flush your stuff to disk. So by that, your state is all on the primary node. That's why I'm not doing iSCSI multipathing between the two physical boxes at the moment, because I think my head just gets and I end up missing something, and I'd rather kind of take it one step at a time. But yes, C, standard.
Any intention to put maybe some like hot drives in between storage, sort of between, like not that you can get much faster than anything. Maybe the cheaper 750s are like, yeah, well, you can die, you can be in a raid.
So it's funny, yeah. So 750s. I just got my prices for those. I'm putting an order in next week for the 8, I think, because they're a little bit cheaper. So our virtualization, we don't use any local storage at all. There's no caching that's happening there. It's all on the server side, and because we're using relatively modern kernels, the iSCSI stack and layer that does iSCSI is actually much more efficient than it used to be. So you'll find a lot of stuff doesn't really come back to the VM or to the hypervisor. You'll find it actually sits back on storage servers.
So probably just having more RAM in storage servers.
No, this RAM. That's something I didn't pick up. The storage servers use the absolute base model V3 Xeons. They're 1.9 gigahertz. They're the cheapest chip. Well, they're overpriced, but they're cheap. They're really, really cheap. They only have 32 gig, which is like kind of the minimum I thought for those. And they're using like 4 gig a node, 4 to 6 gig, because it's so low latency. You're not caching anything in RAM. You don't want to cache stuff in RAM. Not if you can help it.
With my NASA phone's running RFS and with my friends, I give it, it'll use it.
The more RAM you have, something better, right? Unused RAM is wasted RAM.
It's like just the TV
this is a bit different.
Watch that it's caged, whatever.
Yeah. All right, cool.
Sam will be around for a bit.
Yeah.
Afterwards to answer any more questions. Next up, we're going to roll the Chromecast dice, and Ricky.
Do you know? Okay, I think I figured it out. So
Ricky's going to talk about containers without containers.
Right. Cast. I love the two things. Truly, yeah. Good luck in God's food. I just have to get the speaker notes actually. Yeah, I had those. I just didn't know them. I can do this in the next. No. Oh, look, Chromecast crashed. Okay, so it probably doesn't work with Chromecast and the speaker notes.
Choose one.
Just wisely. No, press the thing that doesn't look like you should press it in the top right-hand corner of that window. The little arrow thing. So you press, oh, it's gone. Stop it. You press this arrow thing. That's hidden. You wait for it to finish beach balling whatever it's doing. God. There you go, and then you press this one. And then you press this one again. And then that one. And then that one. Oh, that's already crashed. There's your engineer. You're running out again. Press that one, and then bottom one. And then you press the top option. Yeah. And then you press the input to bring up that screen.
So I was to say we can get a discount on Chromecasts. Anyone's in?
I have one of
Well, there's offers. It's like chromecast.com/offers.
Yeah, it's got the, what?
Nice.
You can present on my laptop screen if you would like. It's small. If only an HDMI cable existed.
We should blame the cloud.
Always like, oh man, we're gonna use clouds, like place clouds on someone else's computer. Hey man, we're gonna like save money by putting our files on someone else's computer. Everything wants that. Data government wants that.
If you haven't been to an Infracoders before, I've never seen this happen. HDMI is really reliable.
First time
Yeah.
Your website. Like clouds.
It's just refusing to do.
Just put your speaker notes on it and just talk. Will probably suffice.
Yeah. Don't need the slide.